In recent years, the world of astronomy has been abuzz with an exciting and mysterious discovery, the potential existence of a ninth planet in our solar system. This planet, if it truly exists, could be as large as Earth and is thought to be coming back into our solar system after being absent for thousands of years. The idea of an unknown planet lingering in the outer reaches of our solar system has fascinated researchers for decades, but it is only now that we are beginning to gather concrete evidence to suggest that such a planet might actually exist. The researcher leading this discovery is Mike Brown, a professor of planetary astronomy at the California Institute of Technology, who, along with his colleague Constantine Batygin, has provided compelling evidence of the existence of this mysterious ninth planet. Mike Brown is no stranger to controversy and groundbreaking discoveries. He is famously known in the astronomy community as the Pluto killer because of his instrumental role in the decision to reclassify Pluto as a dwarf planet in 2006. This decision was a significant shift in how we view our solar system. For many years, Pluto was considered the ninth planet in our solar system, but in 2006, the International Astronomical Union, IAU, changed its status, declaring that Pluto no longer met the criteria to be considered a full-fledged planet. Instead, Pluto was reclassified as a trans-Neptunian object, TNO, a term that refers to objects that lie beyond Neptune's orbit. With this reclassification, the position of the ninth planet in the solar system remained vacant, and for nearly 2 decades, scientists have speculated about the possibility of a mysterious ninth planet. Brown and Batygin's research into this subject has been ongoing for several years. The two scientists focused their attention on the Kuiper Belt, a vast region located beyond Neptune's orbit. This area is home to a large number of small icy bodies, including dwarf planets like Pluto, Haumea, and Makemake, as well as thousands of smaller objects collectively known as TNOs. These TNOs have long been a subject of interest for astronomers, but in recent years, some of these objects have exhibited strange behaviors that suggest the presence of an unseen, massive body in the outer solar system. Specifically, Brown and Batygin noticed that several TNOs appeared to be influenced by the gravity of an unseen planet, causing their orbits to behave in ways that could not be explained by the known gravitational forces from the Sun or other planets. The evidence they discovered was compelling. The orbits of these TNOs seemed to be clustered in a way that pointed to the gravitational pull of a massive planet located far beyond the known planets of the solar system. This led Brown and Batygin to propose the existence of a new, ninth planet. They theorized that this planet could be about 10 times the mass of Earth and could be located in an elliptical orbit that takes it far beyond the orbit of Neptune. If this planet exists, its orbit would be so large that it could take up to 20,000 years to complete one full revolution around the Sun. This elliptical orbit would mean that the planet spends most of its time far from the Sun, making it very difficult to detect with current telescopes. Despite the planet's distance from the Sun, the gravitational effects it exerts on other objects in the solar system could still be detectable. Brown and Batygin's mathematical models and computer simulations showed that the gravitational pull from this hypothetical planet could explain the clustering of TNO's orbits and the observed anomalies. They proposed that the planet's gravity is strong enough to cause these objects to move in specific patterns, creating a kind of gravitational hollow in the Kuiper Belt. This discovery, while indirect, provided the strongest evidence yet for the existence of a ninth planet. However, proving the existence of this planet remains a significant challenge. The planet is so far from the Sun that it is incredibly faint and difficult to detect, even with modern telescopes. The outer reaches of our solar system, where this hypothetical planet is thought to reside, are incredibly cold and dark, with very little sunlight reaching these distant regions. This makes it hard for astronomers to directly observe objects in this area, especially those that are as small and faint as a planet located so far from the Sun. Furthermore, the highly elliptical orbit of this potential planet means that it is often far beyond the reach of even the most powerful telescopes. To overcome this challenge, Brown and Batygin have relied on indirect evidence, particularly the behavior of TNOs and their strange orbits. Through detailed simulations and calculations, they have been able to narrow down the region of space where this planet is likely to be located. They have also proposed that the planet is likely to be located somewhere between 400 and 800 astronomical units, AU, from the Sun, a distance that is far beyond the orbit of Pluto, which lies about $40 Australian from the Sun. At such distances, the planet would be extremely faint, and its light would be too weak for current telescopes to detect. While the evidence for the existence of this ninth planet is strong, astronomers still face the daunting task of actually finding it. Fortunately, there are new technological advancements on the horizon that could help in this search. One of the most promising tools in the search for Planet 9 is the Vera C. Rubin Observatory, which is currently being built in the Chilean Andes. This state-of-the-art telescope is equipped with cutting-edge technology that will allow astronomers to scan the night sky with unprecedented speed and accuracy. The Vera Rubin Observatory's 8.4-meter telescope will be able to survey large areas of the sky in a short amount of time, making it much easier to detect faint and distant objects in the outer solar system. Once completed, the Vera Rubin Observatory will be able to track the movements and patterns of TNOs with incredible precision. By doing so, astronomers hope to narrow down the location of Planet 9 and eventually confirm its existence. Brown and Batygin have already used their simulations to predict the areas of the sky where the planet is most likely to be located, and they are hopeful that the new telescope will be able to find it within a few years. If Planet 9 is indeed out there, the Vera Rubin Observatory may be the key to unlocking the mystery of its existence. The discovery of a ninth planet would have profound implications for our understanding of the solar system. It would force us to reconsider our current models of how the solar system formed and how its various objects interact. For centuries, astronomers believed that the solar system consisted of just the 8 planets, with Pluto being relegated to the status of a dwarf planet. But the idea of a ninth planet, one that has remained hidden for so long, challenges our assumptions and opens up new possibilities for exploration and discovery. It also raises the question of whether there could be even more planets in the solar system that we have yet to detect. As technology advances and our ability to study the outer reaches of the solar system improves, it is entirely possible that we may uncover even more hidden planets or celestial bodies lurking in the darkness. The search for Planet 9 is not just about finding a new planet, it is also about understanding the history and evolution of our solar system. The fact that such a massive object has remained hidden for so long suggests that our solar system is far more complex and dynamic than we once thought. It also suggests that there may be other objects lurking at the edges of the solar system, waiting to be discovered. In a way, the search for Planet 9 is a journey into the unknown, a quest to uncover the secrets of our cosmic neighborhood and to better understand the forces that shape the solar system. At the same time, the search for Planet 9 also highlights the power of mathematics and computer simulations in modern astronomy. Brown and Batygin's work is a prime example of how advanced mathematical models can be used to make groundbreaking discoveries. Just as astronomers in the past used mathematical predictions to discover Neptune, the same techniques are being employed today to search for Planet 9. It is a testament to the power of human curiosity and ingenuity that we are able to search for objects so far from our reach, and it serves as a reminder of how much we still have to learn about the universe. Despite the excitement surrounding the discovery of Planet 9, not all astronomers are convinced that it exists. Some researchers have proposed alternative explanations for the orbital anomalies observed in the TNOs. One such theory suggests that the gravitational effects of the many objects in the Kuiper belt, including Pluto and other dwarf planets, could be responsible for the observed clustering of TNOs. According to this theory, the combined gravity of these objects might be enough to explain the unusual orbits without the need for a massive, unseen planet. While this theory is intriguing, it has not yet provided a definitive explanation for the anomalies observed, and the hunt for Planet 9 continues. As we move forward in our search for Planet 9, the excitement and anticipation grow. The discovery of this hypothetical planet would be a monumental achievement in the field of astronomy, one that would reshape our understanding of the solar system and our place in the universe. It would also inspire future generations of scientists to continue exploring the farthest reaches of our cosmic neighborhood, seeking answers to questions that have eluded us for centuries. The search for Planet 9 is a reminder of the vastness of the universe and the boundless potential for discovery that lies just beyond our reach.